Thank you very much. It's a great honor to be able to speak to you today about some of the work that Symbotic is doing in the robotics space. Before I start, I always like to reflect on the computer, obviously the most complicated machine that humans have invented. And today's computer, of course, cannot be designed without a computer. And to me, embedding that into a physical system, of course, starts with my childhood inspiration when I was 8 years old, watching Star Wars and thinking that's something really amazing, and we should use computers to move in the physical world. And that's what Symbotic is doing for customers today. We are moving objects, cases inside warehouses, and really trying to bring AI into the world of logistics for customers. And I'll tell you a little bit more about how that system works. I've spent 30 years of my career working on different kinds of robots, and so bear with me as I show you some old videos of old robots as inspiration. But I think it really comes down to how do we model physical systems? And at the intersection of geometry and the physics of motion, we have perception and control. And to me, numerical methods, how you apply each of those models into a computer that's digital, is one of the challenges and also one of the great opportunities. Especially, we just saw a great example of leveraging modern machine learning to do something really difficult, like driving in traffic. And for me, I had spent a lot of my career thinking about how do we bring robots outside of factories? So factories have structured environments, and it happens when you try to break that structure and you say, I want to run my robot in an unstructured environment. That means I don't know exactly what's there, and I don't know what obstacles are there. And if I do that, it creates what I call the research snowball. So you say, okay, I don't know what objects are there, and that means I can't use pre-planned trajectories or a priori models. So that means I have to use online perception and perceive what's there in real time. And that means, if I'm doing that, it means I can't use predefined trajectories. I may have to adapt my motion and plan something new dynamically in real time because I have new obstacles that I just perceived. And that means that I also may have to not rely on a predefined sequence of tasks. I have to do actually dynamic tasking to do a complicated sequence of motions. And so that ends up meaning that I wanted to relax one assumption, which was, can I use unstructured environments? And now suddenly I have this giant research snowball that's really hard. So I started working on this years with lots of different humanoids, and I wanted to show you sort of an example of, now we see humanoid robots all the time, they go viral, but what it looked like 25 years ago when you're trying to run on a Pentium PC, and this was the first processor actually that got 1 gigahertz. But this is kind of what it looked like, and we actually had a world record for stair climbing on this old humanoid at the University of Tokyo. What we were using at the time was what I like to call search-based AI. So exploiting the fact that Moore's law is leading to doubling of computer performance every 18 months, which has been very consistent over the past 30, 40 years. It means that you're able to reason about the consequences of actions. And of course, the famous example was 1997 when Garry Kasparov was defeated by IBM's Deep Blue. Now, IBM's Deep Blue could analyze 200 million chessboards per second. That's not the way humans play, but it's very, very effective. And now, most of us will be easily defeated by a free chess app on your phone. Because all of us essentially are carrying around a computing device in our pocket that's more powerful than the most powerful supercomputer that existed 15 years ago. And now we're seeing a rise in learning. So learning is actually another example of search-based AI, because what you're doing is you're running an optimization function when you're training a neural network. You're minimizing a loss function, and you're exploring a parameter space, tuning a neural network. It requires a huge amount of compute, but that's OK, because now we have cloud computers. So when you think about a planning problem and breaking it down into graph search, 30 years ago, the best planners that could run in real time in unstructured environments were navigation planners, because you could discretize the search space into a grid, run your favorite classical AI search algorithm like A* or Dijkstra's algorithm, and you can get optimal paths. But what happens when you have higher dimensions? And so this is a simple example of a three-dimensional robot arm, 3 revolute joints. You could model this in a 3D joint space. And if I added a single obstacle in this space, like a pole that the arm had to move around, even though it's a very, very simple geometry in the workspace of the robot, when you map that to the configuration space, you get actually a really complicated shape, a configuration space obstacle that's really, really hard to model. And so at the time, we were looking at how do we control a hyperdimensional robot like a humanoid or a 7-DoF manipulator arm without having to discretize the entire configuration space in memory, which you couldn't do. And the way that we came to a solution was, well, we don't need to store the entire space. We can just sample it, because we can do a collision detection and we can see if the robot is hitting anything and then build a search tree. So I was able to collaborate with my colleague Steve Laval, and we built what we call a rapidly exploring random tree. So this was one of the first sampling-based planners that was single query, and it would apply to a lot of different problems. And I think one of the reasons that was nice about this algorithm was that it allowed you to quickly explore a space, but in the limit, guarantee that you would explore the entire space. So that meant that you could build a search algorithm that was incrementally constructed. You didn't have to pre-process the space at all. That means you could have a dynamic environment that's unstructured and unmodeled. You have very few parameters to grow the tree. And the nice property is that it's biased to explore large Voronoi regions of the space. So in mathematics, you really want a search algorithm that doesn't get stuck in local minima. It's actually able to branch out and cover the entire space. So we actually proved mathematically that it can cover any non-convex space in any dimension. And so when you apply that to a 7-dimensional robot doing manipulation, here we did online perception with a stereo camera. You can calculate a collision-free trajectory to grasp this bottle in real time. And then we were able to basically build one of the most expensive beverage delivery systems in the world. But the idea would be then is that this is very scalable. It means you could place the robot in any environment and then have it walk around and manipulate things without having pre-planned motions. So I've spent a lot of time adapting this to footstep planning and navigation and quadrupeds and bipeds. And right around that time, there became a huge interest in automated driving. So you heard Jamie talk about now how much it's involved. I was one of the original founders of the Google self-driving project, which is now Waymo. I hope you guys get a chance to ride some of the Waymo cars today. But one of the things that we learned was that you need a planning system and you need some rules in order to make a safe system. And I think Jamie mentioned one of the challenges is how do you combine learning where you don't have very good explainability and a system that's designed where you can actually have some safety guarantees. So after Google, I joined Toyota and spent 10 years thinking about how we could build automated driving systems that were safety certifiable and that you could actually ship neural networks into production. And we were able to actually do that with our teammate. So in 2020, we released the very first Lexus and Toyota automated driving system called Teammate that actually has ramp-to-ramp, hands-off automated driving on highways with neural networks in production. That was a lot of work, and and a lot of fun, but I think we're just getting started, and I think we're going to see a lot more automated driving technology expanding in the world. And so that made me think, after 10 years at Toyota, what I could do next in terms of trying to bring robots out of factories. And I was fortunate to be able to connect with Symbotic. Symbotic, I want to tell you a little bit about this company. We are delivering to customers an end-to-end automated warehouse system. Right now, most warehouses have a lot of conveyors and sorters and a lot of people that are manually depalletizing pallets, sorting inventory, repalletizing, and shipping out to stores for consumer packaged goods, foods, basically everything that consumers need in the world to live their lives. And Symbotic's been at it for a long time. They're actually 18-year history trying to do product market fit. And this is a really hard problem because it is, the warehouse is semi-structured. You know, you don't have to deal with snow and rain like you do on an automated driving traffic scene, but there's a lot of variation. There's damaged packaging, there's all kinds of uncertainty and noise that you have to deal with in order to make a system that actually works. So I want to tell you a little bit about our system and a little bit about our robots, and more excitingly about how we're combining both planning and learning in a novel way to make a reliable robot system work. This is an example of one of our modules. So a single module of our system is 10 levels. We can store about 1 million cases. We call boxes, essentially, 24 by 24 by 18-inch boxes. That covers, over 90% of all the ambient goods you would ever buy in a store like Target or Walmart. And it has a multi-level buffering structure, and we would populate each level with about 40 bots. So you get over 400 robots in one of these modules, and everything is fully automated, the inbound and the outbound, which I'll describe. The easiest way is to show you just sort of this is a modern distribution center. We have automated palletization and depalletization. So a pallet of goods comes in, it gets singulated. If it needs to, it'll get automatically tipped so that we can store it more efficiently in the structure. We have a very large shelf system and a car-like robot, a fleet of them, that basically manages and keeps track of all of the inventory. And one of the things that's nice about our system is that everything is completely algorithmic and software driven, so we do automated storage and sortation for customers. So you can just inbound everything in any order. We can sort it and palletize it automatically for customers. And we have a very rapid, automated, cooperating dual-arm system to build 8-foot high pallets that are very tall and 50% more dense than what you could build if you tried to build a pallet manually. The inbound storage essentially takes pallets off of trucks and then automatically singulates them. We scan all the barcodes, we image every single side. We basically build a complete digital twin of every single box in the entire inventory. And for a modern system at one site, we will have maybe 4 modules. So we will have maybe 3.5 million cases storage capacity in one site. And that would have over 1,000 bots distributed across the 10 levels managing that inventory. The inventory is able to take advantage of similar packages. So when you have 3 packages, for example, that are the same size, the robot's able to actually handle 3 of them at the same time. We call that carpooling. We have a flexible buffering structure, so we're able to basically handle any kind of variety of packages. And because we do underpicking, we can handle a variety of shrink-wrapped or other boxed goods very easily. This is the bot hardware. We have a very fast energy-absorbing ultracapacitor, so it can top up its battery without ever having any downtime for charging. So the bot basically can run 24/7 with no time needed for charging. We have essentially a little forklift that's configurable in the payload bay so that we can carry up to 60 pounds in a variety of packages. This is the case handling mechanism. As I mentioned, it's very flexible and fast, and while we're picking and placing, we basically can top up the battery and keep it constantly charged. One of the most exciting things that I, as a planning algorithms person, got really excited about was how do you coordinate the tasking and the routing and the inventory management of the entire fleet of 1,000 bots. And you're managing, let's say, a 3.5 million inventory storage system at one site, and you have to process 200,000 boxes a day. So I'll tell you a little bit about how we do that. We have an outbound cell that every day a store will order, I want this amount of inventory, and we will sort that inventory and outbound it, and we have the fastest automated system for outbounding mixed SKU pallets in the world. And one of the key advantages of our system is that we're able to sort the inventory on the outbound. And what I mean is we are able to build what we call Symbotic smart pallets. So normally, if you are going to go to a distribution center and you're going to outbound a pallet to customers, essentially what you will do is you will basically do 3D Tetris, and you will build this pallet kind of like what you'll see here on the left. A traditional mixed SKU pallet will have whatever fits and is stable, and you have to look at all the constraints, like you don't want heavy cases on top of light cases. You have to have toxicity constraints where you don't want to put motor oil on top of food items. So you have to manage all of these constraints, the crushability of the packaging. Our system does all of that automatically. And what's even better is that we have a digital map of your store. So we actually know exactly which aisle every item that you ordered goes in. So most customers, if they're taking a traditional mixed pallet, they have a back room in the store because they have to break apart the pallet and sort everything. This goes to aisle 2, this goes to aisle 7, this goes to aisle 5. But we outbound a pallet that's only aisle 5, and the top part of the pallet is the north side of aisle 5. The middle part of the pallet is the middle of aisle 5, and the bottom of the pallet is the south side. So all you have to do is take our pallet, take it to aisle 5, and start unloading. And customers love it. We save so much time and so much money, and our sortation system is basically what allows it. So our computers are using search-based AI. We analyze millions and millions and millions of ways you could build this pallet. It's like playing 3D Tetris, right? And the computer can optimize and build a pallet that's taller and more stable and more dense than any human could ever imagine trying to build. So then once you have that algorithm all connected, how do you make this system actually work? I'm just going to look at one level. So imagine you have 10 of these levels stacked up. We have up to 150 bots that have to share this space and deliver and outbound thousands and thousands of cases every hour. So this ends up being a really, really hard multi-agent planning problem. So here's an example of just one level where we are in real time tasking and routing every single bot in the fleet to outbound exactly this case at this time at this location. And so it's a huge ballet that needs to be coordinated. And why is this hard? One of the reasons is we have these very long, narrow corridors to access cases. We have a very compact deck where the robots move between aisles and outbound driveways. And we have these very short but very busy driveways because all the robots are trying to basically, as quick as possible, deliver that case so that the pallet can be built in real time. And we build a 250 case pallet almost every 7 minutes in our system. We also have very fast bots. They go up to 25 miles an hour, faster than almost any autonomous mobile robots in a warehouse or factory, and they have car-like steering. So it's nice because most autonomous robots that are holonomic, if they want to make a 90-degree turn, they have to come to a complete stop. But our systems have car-like steering, so they just go very quick. It's a large, complex fleet. There could be communication delays, there could be execution deviations, or you have to make emergency stops. And essentially what it boils down to is a very traditional classical multi-agent pathfinding problem. If you've ever looked at a traveling salesman problem, this is a multi-salesman traveling salesman problem that is really, really hard. It's proven to be NP complete and NP hard, so just forget about trying to get an optimal solution, right? The only solution that's practical is going to be something that you're sacrificing optimality, but the good news is there are algorithms that exist. They're non-optimal, but they're practical and they're real-time. So I want to tell you a little bit about our system and some of the choices we made to make this actually work, which is really, really hard. Today, every single day, we have a fleet of over 20,000 robots that are moving over 7 million cases. So we're doing a huge amount of work for customers every single day. And we use a version of multi-agent pathfinding that is based on priority-based search. I'll tell you a little bit about how that works. Essentially, it's a two-phase algorithm. So we have a global coordinator that routes and tasks each of the bots, and then we have a single bot path planner that finds a collision-free motion for every single bot. So for example, one of the tasks might be, go fetch this case and deliver it to this outbound driveway. And usually there's a time limit, so it has to do it within 4 minutes. And that's part of the reason why this constrained planning problem is quite hard. So how do you actually do this? How do you decide which bot to plan, and how do you deconflict the paths of the robots? Now, normally you could plan very quickly every bot, ignoring all other bots. So you build a path for every robot, and you calculate it based on the time optimal solution for a single bot, ignoring every other bot. And then you add a priority between each of two robots to resolve a conflict, meaning that if you have two bots, you'll say, okay, bot A has a higher priority than bot B, so I'm going to plan bot A's path, ignoring bot B. And then bot B is going to basically plan its path while A is now a moving obstacle for bot B. So it may have to take a little bit longer path because it has to yield to whatever bot A is doing. Now, it turns out if you try to scale this to 150 bots, you actually can get into deadlock situations, which is really, really hard. And it's part of the challenge of building a complete system that can guarantee an output, and one of the things that Symbotic has spent years figuring out. But one of the nice things is that if you frame this as a classical search problem, you can actually build a tractable solution, and you can find complete plans. So the single bot planner will optimally plan single robots while avoiding the higher priority bots. And what this looks like is, let's say we have two bots. Here's a simple two-bot example of priority-based search. So I'll plan both of these together, ignoring the other bots. And as you can see, we immediately see that in this example, both of these planned solutions overlap each other, and the bots would hit each other if I tried to execute that plan. So instead, what I'll do is I'll identify the conflict and what time it happened, and then I'm going to assign. Right now, let's just say I assign a higher priority to bot 1. So first, I will plan bot 1's path, and then that bot becomes a moving obstacle to bot 2. And now, when I output that plan, I can now execute both of these plans in parallel, and I get a complete solution for this two-bot planning problem. And then, to extend it to a higher number of bots, let's look at how this would pan out. So let's say I have now 4 bots, and I'm planning their solution, and what I will do is I will keep track of all the conflicts. So in this case, there were 3 conflicts, and I will keep track of which one happened earliest. And then I will try to prioritize bot 1, and I will also try another alternative is prioritizing bot 3. So I take those 2 examples into a search tree, and I will say, okay, first I'm going to deconflict by prioritizing bot 1, and now I have another conflict, bots 3 and 4, and do the same thing for this side. I deconflict the first conflict, and then I keep track of when I get another conflict. And now, essentially, you can basically keep going down the search tree. So let's assume that this one has a better heuristic. And now I'm going to say I have an earlier conflict with bots 3 and 4. I will do the same thing. I'll prioritize bot 3 and then see what happens. If I prioritize bot 3, now I actually get a complete solution to the whole 4-bot problem. So essentially, I found a solution in this case. So if you put this all together and you extend it out to 150 bots, right, you will get the Symbotic multi-agent planning system, which we have evolved, and this is just show you an example of the past couple years of performance. So we had an original router that was called the Beltway router, and you can kind of see robots going clockwise around the top part of the deck, and you can see a lot of robots hanging out in the middle while they're trying to cross traffic, essentially. With TSR, which is the time-space reservation router, the most recent example of our algorithm, we're able to get bots moving a lot faster. We can also utilize much more of the free space, and our most modern version, we call the TSR Executive, basically is able to modify a path that we plan for the whole fleet every 100 milliseconds and make sure that it's all collision-free, that we can't take advantage of any uncertainty. And we've been able to basically, with an over-the-air software update, deliver up to 30% higher performance for a fleet without any hardware changes at all. So our customers are really happy about that. We are moving over 2 billion boxes a year now at Symbotic. We have over 40 operational systems and over 20,000 robots, and there's a huge backlog of demand for our system. And one of the most exciting things is I believe we're just getting started. So I've shown you a kind of classical AI search-based approach to solving a multi-agent planning problem in the real world, which is very, very hard. Of course, there's a lot of details I left out, and I just joined as CTO in January, so I'm standing on the shoulders of giants of all the people at Symbotic who actually did most of this work. But one of the things I've been really excited about is I actually believe that we're on the cusp of refining the systems to the point where my dream of having robots in unstructured environments is going to happen very soon, because we have now the best compute, the algorithms, and we have machine learning technology that can scalably process data to the point where we can build these systems that are actually working and reliable and can adapt to uncertainty. So I want to reflect a little bit about how do you combine a model-based system with machine learning. And in fact, a lot of us were excited about an example of that happened a couple years ago when AlphaGo came out. Everyone focused on the machine learning aspect of AlphaGo. But if you actually read the paper, it's a priority-based search tree. It's a Monte Carlo search tree. So it's a classical search tree like the IBM's Deep Blue. It's just that it's learning the heuristic, right? It's not a hand-coded heuristic. The heuristic is trained off of human Go data, right? And that's the trick. You can combine a classical search algorithm with learning. So you can build then a system that has bounds on its behavior while taking advantage of the power of machine learning. And Jamie brought up the challenge of explainability. I actually think that's a really big problem. Like, how do you make sure that when you train a machine learning system, it does what it's supposed to do, and you can guarantee safety? That's a really, really hard thing to do. But I think there's hope, because now we can actually combine our models and use machine learning to fill in the gaps of those models. All of the parameters that were really, really hard to estimate, and why things were brittle was because people had no way of learning those parameters and adapting in the real world. So what I'm excited about is using simulation. We saw great examples of using generative AI to do sim to real or domain transfer. I think this is really, really powerful. How do we use simulation to build essentially artificial synthetic data where real data is too hard to get, right? And we can combine a model of a system in two different ways. One model's analytical. Equations. That's like bread and butter for robotics engineers who were trained in my era before the internet, right? It's like, I want to make a Lyapunov function, and I used to program robot helicopters. And I could say, I could guarantee the stability of this control system up to amount of wind, noise, and disturbance, and guarantee a stable output of that system by using mathematics. However, it was very hard for me to estimate the friction of a rotor, right? That's something that a machine learning system can do much, much better. So we can use a statistical model combined with an analytical model to build a better robot system. And so I thought about this deeply, and it actually comes down to what I think a machine learning system is actually doing. People use the term AI all the time, but let's think about what does it mean to be intelligent, and what does it mean to have experience? So if I asked you a question, I said, if you wanted to go downtown in Manhattan, and there were two drivers you could choose from. One of them is a chess prodigy with an IQ of 200. The other is a New York City taxi driver who didn't graduate high school, but in 50 years never had an accident. Right? Which one do you want driving you? Right? And I think it brings up my point that planning, logic, reasoning provides a machine with intelligence and reasoning capability. But machine learning is providing experience. So I actually think a better word for machine learning is artificial experience, because that's actually what is very important. And in fact, we have another word for that in human culture. When we talk about somebody who has life experience, we call them wise. So I would say we want to train robots that actually have artificial wisdom. Right? We want to give them enough experience in a task that they are wise. They make the right choices, even though they also have planning and logic and reasoning capabilities at the same time. So as I reflect on the future, I really think about how do you build a safe system that combines safety and reliability together. I always ask people, you love end-to-end learning, right? I think it's really exciting, but it has some real problems. If I told you, I'm going to give you a parachute, and I trained a neural network to deploy at the right time, are you going to jump out of that plane? How do I guarantee that it'll do the right thing? And you might ask me, can you guarantee that it'll do the right thing? And I'll probably say no. And then you'll ask me, well, what happens if it fails? Why did it fail? And I would say, I don't know. It's a black box neural network that I trained. And then I would say, how are you going to fix it? And I would say, more data. And then you would ask, how much data? I don't know. Right? So we end up getting in this problem where if we want to actually build robots that we can control, and the robot doomsday that everyone's worried about won't happen, we can do that by building a responsible system where at the very top level of a robot behavior, I believe we should have a human design system that bounds the behavior of that system. But it's completely fine to have a machine learning system that learns parameters of that model. Right? And that, to me, is a much more responsible way to develop an intelligent machine. And basically, as you all know, if you've worked on robots, you could have the best software in the world, but if your hardware is flaky, you're going to have a bad robot. And vice versa. You could have an amazing piece of hardware, but if your software is buggy, it's not going to do the right thing. So I used to tell my students, building a robot is one of the hardest things you'll ever do in your life. It's going to kick your butt. But when it works, it's really, really gratifying. But we need both. We need robust hardware and robust software to make a reliable robot. And that's something that I'm really excited about because we now have better tools for doing that. Better sensors, better compute, better algorithms, and huge amounts of data. And putting that all together, I do believe this is absolutely the most exciting time right now to be building robots. We can use these best-in-class tools to do continuous integration, deployment, and testing. When I joined Google, it was 2008, and there were only a handful of companies at the time who had enough resources and capital to build their own data center. So my old lab at Carnegie Mellon, I had desktop machines that I was trying to run planning algorithms on, and then you go and suddenly you have access to a data center, and you're like, wait, what? I have unlimited CPUs and unlimited storage? Oh, that changes the way you think about a problem. And that's something now everyone can use because we can use cloud as a service. So you don't have to build your own data centers. You can use advanced compute and advanced storage and advanced networking capability as a service and only pay for what you use. We should fully leverage what computers are good at. And I mentioned before, what are computers good at? In my mind, billions of calculations per second and processing huge amounts of data. And that's essentially what a neural network is doing. Like I said, what is the difference between optimized gradient descent and training a neural network? Not much. They're basically the same thing. And you can use simulation and emulation to generate data where you don't have data. And we saw a great example of that in the previous talk, generated synthetic traffic data that might be otherwise too dangerous to generate by yourself. So how do you make a robot more reliable? I can synthetically generate the long tail of difficult situations and artificially increase the probability of them happening. So for example, if I want to make sure that my autonomous car can handle a baby carriage in an intersection, I don't have to drive for 10 years and millions of miles just waiting randomly for some pedestrian with a baby carriage to walk in front of my car. I can synthetically generate it and artificially increase the probability of that happening to make sure that the system can handle every single situation. So to me, I think this is really, really exciting for how we can actually leverage statistical models and increase their ability to be robust because we can synthetically generate the long tail of low probability but high risk events. We don't have to make a choice between a classical planner and machine learning. We should do both, in fact, just like AlphaGo does, right? Monte Carlo search with a learned heuristic. It's perfect. And that's actually what Symbotic is doing. We're fully embracing a classical multi-agent path-finding algorithm, but we're learning all the heuristics to make the system more performant. That means I could take a customer's order data and I can calculate what the optimal sequence should be as a heuristic so that I can outbound everything much more efficiently. And finally, I've been thinking a lot about how to leverage modern compute to make fleet intelligence. And to me, one of the greatest opportunities is to utilize the cloud to do proper fleet learning and fleet intelligence so that the systems can improve. One of my colleagues at Carnegie Mellon used to ask me, James, I know this machine learning algorithm is going to work. It's just that my robot breaks down before I have enough data. So instead of running one robot for 10,000 hours, let's run 100 robots for 100 hours each and get the same amount of data much faster. So fleet intelligence and transferred learning is going to be a big game changer. Thank you very much.